Problem 3 is a historical application. It says use linear approximation to estimate the cube root of 63.7. Compare your answer to a calculator approximation of the cube root of 63.7. So this is a really, really neat problem that I personally enjoy very much, because many of you, probably all of you, don't remember a time in your lives when a calculator maybe didn't have a cube root function. But how in the world did we figure out what the cube root of 63.7 was before computers and before calculators that we all, or our smartphones will do this for us? And the answer is we could use linearization for an example like this. So what we would do is we would find the linear approximation for a value really close to this number, and then we would plug 63.7 into the line, and just through traditional arithmetic, you could estimate out through several decimal places what the true value was. So the first thing we're going to do to see how this is done is we're going to find the appropriate function for f of x to use for your approximation. So what should our function f of x be that we base this on? So if I'm looking at the structure, 63.7 most likely was plugged into the cube root of x. So we're going to let f of x be the cube root of x. Since I know I'm going to have to take some derivatives, I'm going to rewrite it as x to the 1/3. Now we need to find a value a to use for our approximation. And remember, a needs to be a value that is close to 63.7 so that the line is a good estimator for the graph, but it should be one that we can calculate quickly without using technology. So we need to think of, are there any cubes, perfect cubes, near 63.7? And the answer is yes, 64. And you can always test your value of a by plugging it into the original function, which we're going to need to do anyway to come up with our line. So f of 64 is the cube root of 64, which is 4. So the point on our line is 64, 4. Now we need to determine the linearization. So for the linearization, I have my f of a, but I also need to get f prime of a. So let's take the derivative. And this is where this form is a little bit easier for the derivative. So 1/3 x to the negative 2/3. So now if I plug in 64, and the 1/3 will stay 1/3. We know from our f of a calculation that the cube root of 64 is just 4. So this is now 4 to the negative 2. 4 squared is 16, but the negative means dump it in the denominator. So if I move 16 to my denominator, 16 times 3 is 48. So the line that I want is f of a, which is 4, plus f prime of a times x minus 64. So this line can be used to estimate the cube root of x for values of x that are near 64. Part D says, okay, put your money where your mouth is and use the line to make a good guess. And we want to round our answer to 5 decimal places. So we get 4 plus 1/48, 63.7 minus 64. And when I round this to 5 decimal places, I get 3.99375. Now part E says, this method was very important before calculators were widely available, because all of the calculations could be done by hand, even if they were a little tedious. Now that we have calculators, use a calculator to approximate the value of the cube root of 63.7 and round your approximation to 5 decimal places. So let's see what we get when we type it in the calculator. So when we type it in the calculator and round, we get 3.99374. Look how close this is. The reason we had to have you take it out to 5 decimal places was you have to go that far out before you can even distinguish that there was a difference. So the closer and closer your value is to the value of A you chose, the closer we get to 64, the further down the decimal line we have to go before we can even see the difference in these two values. So this is a very, very powerful tool because it is much, much easier to type things into a line than it is to type it into some of these functions, and this could actually be done by hand. If we start to notice that the errors are getting too big, right, or the distance is getting too far away, then that's the clue that we would need to find a new value A and then use that to test values around that. So believe it or not, if you ever take Intro to Statistics, simple linear regression, the equation of the line that you find, the mechanics behind that are calculus. And instead of doing this with a function, we're actually doing this with data. And the whole premise behind simple linear regression is that a line can be a really, really powerful predictor of what's actually happening to something that's much more complicated.